All right. Hi, everyone. Welcome to our 9 a.m. press conference. First results from NASA's new ice measuring space laser. Our speakers today are Tom Newman from NASA Goddard Space Flight Center, Lori MacGregor from the University of Texas, Austin, Ben Smith from the University of Washington in Seattle, Ron Kwok from the NASA Jet Propulsion Laboratory in Caltech, and Joe MacGregor from NASA Goddard Space Flight Center.
Great, thanks for coming this morning. I am Tom Newman from NASA Goddard Space Flight Center. I'm the IceSat-2 project scientist. IceSat-2 is recently on orbit. We launched September 15th. We've been up for about 90 days, and we've been getting phenomenal data that my colleagues are going to show you in the next couple of slides. It's really been working well. IceSat-2 carries a single instrument. It's called ATLAS, the Advanced Topographic Laser Altimeter System. And it's a LiDAR that's up in space. What it does, it sends out small pulses of laser light. It generates a single pulse that's split into 6 individual beams, and it precisely times how long it takes that light to go from the satellite down to the Earth and back again. So that range, or that time of flight, is its primary measurement. When you combine that with the knowledge of the position of the satellite from GPS and the pointing direction of the beams, what you can do is derive the elevation of everything that IceSat-2 flies over. So the height of the ocean, the height of ice sheets, the height of sea ice, the height of forests, all around the world. Now what makes IceSat-2 really cool is that it sends out really weak pulses of laser light, and it detects individual photons as they come back. So it's using single photons to make these elevation measurements. The laser on ATLAS fires 10,000 times a second. So in each of those 6 beams, you're getting 60,000 measurements every second, 60 times a minute, 60 minutes an hour, 24 hours a day. It's a phenomenal data set. It's really a huge data set. As the name suggests, there was a first IceSat mission. It was on orbit from 2003 to 2009 using a similar technology. And based on the success of the IceSat mission, the National Academy of Sciences in 2007 released a report giving direction to USGS, NOAA, and NASA about what they should be working on for the next decade. And based on the success of IceSat, they said, we want more of that. That's such a powerful tool and such a great data set. NASA should be doing more laser altimetry from space. And so over the past decade, that direction turned into IceSat-2. As I said, we've been on orbit for about 90 days and been collecting data for the last 60. And at this point, I'll turn it over to science team lead Dr. MacGregor to show us some early examples. It's really cool.
Hi, good morning. I have the pleasure of showing you some sampling of the data that is amazing. I agree with you. I want to get you oriented on how we're looking at the data. And right now we're showing you point cloud transects. So what that means is Tom alluded to every point in this long track measurement of the satellite is a measurement from IceSat-2 or the ATLAS instrument. And each point has an attribute of latitude, longitude, and elevation. So as the satellite orbits the Earth and creates a ground track beneath it, it collects this data along track. So that's the transect. The x-axis, the horizontal, well, that was fast. Okay, that's good. The x-axis is the long track distance, and the y-axis is the elevation. So this is a sample of a ground track over the coast of Mexico. So just for your reference, the Google image is at the top of the screen, and you can see the track in blue, and then the corresponding data to this track is beneath it on the lower half. I like this one because you can see as you're moving down toward the coast, the incline of the terrain, as well as the vegetation on the terrain. And then you get to the coastline and you see the apparent surface of the ocean, but also we're getting returns from beneath the ocean. So because this wavelength is an optical, it's visible, 532, it's a green beam, it penetrates the water surface and we get returns from the ocean floor. So there's a lot of possibilities and potential for shallow water bathymetry with this satellite. It's amazing to think about when you're 300 miles in space and you're getting returns from the ocean floor. I also like this slide because toward the right at the end of the transect you can start seeing the ocean wave surface structure. Here's another example, again, of land and bathymetry. This is over the Suez Canal. So this, again, shows you some pretty amazing penetration of the green wavelength to the ocean surface, and you can start to see the waterway in this area. We have to remember that ICESat-2, these global measurements are going to do a lot for the vegetation community. So we're going to get global measurements of canopy heights and terrain heights. That's what's so amazing about the laser altimetry, is that you'll get returns from the tops of the trees, but the light will get through the canopy and also give you surface returns from the terrain. So we're able to actually derive a tree height at the global scale. This is important because it's a direct measurement to global biomass, and we can improve our knowledge on how that contributes to our climate. This shows an area in Russia, a broadleaf forest, and the top graph shows a length scale of about 25 kilometers, and then we've blown it up a little bit at the bottom. You can see that it doesn't take much imagination to see that terrain under the canopy, so it's going to be a really powerful tool for these accurate tree heights for biomass. Again, ICESat-2 is going to provide another unique measurement capability by a global assessment of our Earth's reservoirs. And this is important because it informs our knowledge or assessment of our planet's water storage. I like this. This is in Washington State, and you can see the two levels of the dam there in the middle of the transect, as well as the sloped topography and vegetation cover along the waterway. And now I'm going to hand it over to Ben Smith, who's going to tell us about land ice and ICESat-2's capabilities.
So thanks, Lori. This is an area that is sort of dear to my heart. This is the Ross Ice Shelf in Antarctica. And on the left, you can see very flat terrain, which is floating ice. And the profile goes over an area called Prairie Ice Rise, which is a marine rise underneath this floating ice that pushes the ice surface up. And so in this flat part, we can see ICESat-2's ability to measure extremely subtle topography. It can measure very small surface slopes. It can measure very small changes in height as it goes over this bump. And then as we get to the right-hand side of the plot, we hit the Transantarctic Mountains, and we find some not so subtle topography. So instead of the very flat area, we're going up over mountains that are more than 2,500 meters tall, and we're resolving every little valley in those mountains. These have been really difficult targets for altimeters in the past, which have often used radar instead of lasers. And they tend to show you just a big lump where those mountains are. And we can see very steeply sloping surfaces. We can see valley glaciers. We'll be able to make out some very small details over all of Antarctica with this. Now, the photon clouds are great, but they're difficult to put on a big map that you're looking down at the top from. So we've started generating the next level of products already, which is an estimate of the surface height from ICESat-2. And we've been filling in this map gradually over the last 90 days. This is, I think, just 3 weeks worth of data showing how much Antarctica has really gotten filled in to this point. So this is showing all the heights over Antarctica from the Ross Ice Shelf to the high Antarctic Plateau. And adding the next 3 weeks of data would basically make this a solid block of color. Now, one of the things that ICESat-2 was really designed to do was to measure surface height changes. So it's supposed to tell us how Antarctica and Greenland are changing as the glaciers, in most cases, are thinning. And so I went to a place where we've been making measurements for a long time, both with ICESat-1 and with other laser altimeters. This is a place called the Dotson-Crossan ice shelves, and Smith Glacier is flowing into those from sort of the lower left, no relation. The middle plot shows everything that we expect to measure with ICESat-2, and this gives you an idea of what those 91 days of orbits look like that we're going to be repeating over and over again. And so you see a very dense network of tracks over there. We should be able to measure an elevation on those every 3 months and get a detailed elevation history for this area. And at the bottom, you can see what we've been up to since 2002, first with some measurements from a NASA mission on a Chilean P3 airplane using a laser altimeter to measure this altimeter to measure the surface height, and then with NASA's IceBridge program from the years in the more recent years, mostly since 2009, I guess all since 2009. And I'm going to show you what the elevation history looks for this area that we can now measure with ICESat-2. So the red stripe now is the most recent set of measurements we've made in 2018. And if we zoom in on the middle of that, you can see ICESat's 3 beam pairs cutting across a track, an early track from that Chilean P3 mission. And if we plot the height section for that, you can see the ICESat-2 track on the bottom. And then you can see the ATM measurement from 2002 and see that in those, 16 years, that piece of ice has lost more than 120 meters. So that area has been thinning aggressively for all of that time. I put the Statue of Liberty in there for scale. She is just under 100 meters tall. Pretty good scale bar for this thing. But if you could imagine a block of ice covering Statue of Liberty to beyond the tip of her torch, that's what we've lost in the last 16 years. And last, I wanted to show you a view, again, from the Ross Ice Shelf, showing the small measurements that ICESat-2 can make. So ICESat-2 has horizontal resolution that's on the order of 20 meters, so across this room roughly. Better if that's what the ice products can do. And vertical resolution that's under an inch. And so we can measure very small features on the surface. This is a trench on the surface of the Ross Ice Shelf caused by melt on the bottom. And we're looking up the trench in the lower view, showing the really incredible spatial and vertical resolution of the satellite. So next, I'm going to turn things over to my colleague Ron Kwok.
Thanks, Ben.
Tell us about the sea ice.
Okay, so, let's see, this one?
Yes.
Okay, so ICESat-2 is designed to do Sea Ice Freeboard, and we get, from Sea Ice Freeboard, we get ice thickness to continue the record of ice thickness from ICESat and other satellites. So Freeboard is the height of the ice surface above the local sea surface. So resolution is very important. We calculate the local sea surface using cracks and fractures in the sea ice cover, and the cracks and fractures, 50%, 80% of the cracks are less than 50 meters. So the resolution of ICESat is very important for picking out the local sea surface for calculation of the height of the ice for calculation of freeboard. So this shows how some of the cracks look like. I mean, they're long linear features, and they're, even though they're all over the ice cover, they're very, very narrow. So this shows a sea ice segment of photon cloud, as Tom was mentioning. Each of these photons are time tagged, and so the range is calculated and height's calculated for every one of those photons. And this ice cover is at 25 meters, and it's levitated because it's not referenced to the sea surface. It's just the reference surface that we picked for this the calculation. And so you can see the density of the photons around the surface. Sea ice is very flat, and the next slide shows how flat the ice is and how good the resolution is for ICESat. So this is a transect of about a segment of 20 kilometers across a bit of sea ice in the Weddell Sea. And you can see very high features and very flat features, which are separating ice flows from each other. Now, each one of these heights are calculated from only 150 photons, and from 150 photons we can get a spectacular flat surface about a little bit more than 2 centimeters, and that's very important for calculating sea ice freeboard. And the other thing I want to point out here, each one of these height segments vary between anywhere from 25 meters and up into resolution. So the resolution is very suitable for calculating sea ice freeboard. And so and also the ice here, the level of the ice is actually referenced to the local sea surface, the mean sea surface, and so it's much closer to zero. So this shows the other feature of ICESat-2 is that we have 6 beams. There are 3 beam pairs. 2 beam pairs each pair has 2 beams that are separated by 90 meters, and the 3 beam pairs are separated by 3 kilometers. So we have very nice spatial mapping of the ice cover over all the ice that we're mapping. And this particular example shows a transition from the compact ice cover in the Weddell Sea, that's in the Southern Ocean, into the ice margin, which is the flattened bits towards the bottom of the slide, and it shows very nicely a transition from that thicker ice into the ice margin and into the ocean. And that's important. An accurate mapping of the marginal ice zone is important because because of the wave and ocean interaction with the sea ice cover, and that's very important for understanding the decay, the retreat of the ice cover during the spring, and also advance of the cover during the winter. And so this and also the cross-track mapping gives us details about spatial variability of the ice cover and details about how the ice cover changes from in time. So this is our first map of the Arctic Sea Ice Freeboard. In fact, we have this is 2 months from launch. This is way better than what we expected. This shows, just to get us oriented here, we're looking down at the North Pole, Greenland's on the bottom, and Alaska's to your left. It shows very high freeboard right next to Greenland, and a gradient across the Arctic Ocean towards Siberia. And at this time, this is the start of the growth season in the middle of October, and we can see the ice edge, and around the ice edge we have very, very thin ice, and that's what's expected because we're seeing the initial growth and advance of the ice cover as the ice cover covers the Arctic over the next month or so. And so we're going to be using this to understand, to continue the record of ICESat-1 in terms of mapping ice thickness and freeboard, as well as the other altimeters. And not only that, this is just the Arctic, and we'll also be mapping the ice cover of the Southern Ocean, and that's going to be a lot of new science that's going to come out of that. So this is a very exciting data set. So I think what I'll do is turn it over to Joe, who'll tell you a bit about IceBridge.
Great. Thank you, Ron. Am I on? I think I'm on. Since 2016, I've had the privilege to be directly involved in Operation IceBridge, which is one of NASA's largest airborne missions, and its principal objective is to survey changing polar ice and bridge the gap between IceSat, which concluded in 2009, and ICESat-2, which launched earlier this year, as you've heard. And we've now had the opportunity to directly underfly ICESat-2 with our most recent Antarctic campaign. These 2 maps here show you the extent of our coverage in the Arctic and the Antarctic over the past decade. And as you can see, we've based out of several locations. We've surveyed many different types of ice, both in the Arctic Ocean, over the Greenland ice sheet, Alaskan glaciers, in West Antarctica, East Antarctica, the Weddell Sea. We've surveyed a variety of regions. And many of these are repeat flights because we wish to observe changes that have occurred on an interannual basis, and in some cases in the Arctic on a seasonal basis as well. So now a little more detail on our most recent campaign aboard NASA Armstrong Flight Research Center's DC-8 Airborne Science Laboratory, shown on the left here, which operated out of Punta Arenas, Chile, and Ushuaia, Argentina. And in the middle here, you can see a map of the 24 missions that we flew in a little over 5 weeks, surveying parts of West Antarctica, the Weddell Sea, the Bellingshausen Sea, to not only observe changes that have occurred since the last time we flew in that region, but to directly underfly ISAT-2 tracks, and also to survey some new regions that our science team is particularly interested in. And on the right, you can see a table highlighted in yellow are the missions that we flew. We always design more missions that we can actually fly given our schedule, so that we can have a geographic diversity of targets and deal with fickle Antarctic weather. But ideally, of course, when we go there, especially if we're attempting to underfly ISAT-2, we have clear skies overhead. So when Operation IceBridge is going around, it's often bluebird everywhere we go, because we've planned it that way. All right, so a few campaign highlights from this most recent campaign. Again, I mentioned 24 missions, which tied our record in 2 previous campaigns aboard that aircraft, which we're particularly proud of because it was our most challenging IceBridge campaign yet. For some of the ISAT-2 underflights that we endeavored to do, we wanted to fly them very close in time, within a couple days of an ISAT-2 orbit in a given geographic region. And in order to achieve that on a daily basis, we're redesigning our flights to find the nearest orbit and then stay within the same geographic region, have the same scientific objective. And we achieved that on several occasions. So we were happy with that. That was challenging. Normally our missions are static before we begin the campaign. Over sea ice, which changes even quite quickly, on an hourly basis even, then we implemented real-time drift corrections by making wind measurements at low altitude. And so that was an additional challenge to be able to survey that sea ice. It succeeded. We flew more than 13,000 miles of ISAT-2 ground tracks, and we also collected numerous other complementary data sets aboard across Antarctica. So we have not just our airborne laser altimeters on board, we have 2 of those. To directly compare to ISAT-2, we were able to add other instruments and collect additional data sets. And I'll show you a couple of examples of those. On the left, of course, we have an example, a laser altimetry swath. So we have a laser altimeter that scans in a sort of circular pattern on the ground, and as you fly along track, you end up with a pattern that looks like that. And this is from the Airborne Topographic Mapper, which is an instrument that's operated over now a quarter century in Greenland and more recently in Antarctica, in predecessors to IceBridge. And you can see we're flying here over crevasse field and measuring crevasses that are tens of meters deep in Antarctica. And that's the kind of data that we can directly compare to ISAT-2. On the right, you see an example of our ice penetrating radar data. So that dark black flat line or smooth line toward the top right is the ice surface, and then that deeper reflector that's quite varied in its topography, in its elevation, that's the ice bedrock interface. So we can directly measure ice thickness. And in the near surface, using a higher frequency radar, we can also measure how much snow is falling over year to year. And our deputy project scientist, Brooke Medley, has actually sort of classified this and compared this to a model, and it seems to line up very nicely. It's a nice sort of quick validation of our efforts there. Of course, just to give you a sense of what it looks like when we're flying aboard Operation IceBridge, it's just a collection of photos from our most recent campaign. You can see the variety of ice surfaces that we encountered. And of course, this is the same variety of ice surfaces that ISAT-2 is encountering. So getting a sense of what those look like in person is nice. And so again, we have crevasse fields, we have different surface textures, we have icebergs. B-46 is the one that recently calved off Pine Island Glacier. We have a variety of sea ice types, and in the top left there, you have a long exposure view from a camera that shows the 2 laser altimeters that we have. One has a narrow swath, the brighter green circle in the middle, and then a wider swath, which is the one you saw in the previous slide. So finally, I'd just like to conclude by highlighting 3 different studies that are relatively recent that leveraged IceBridge data and are maybe particularly relevant to ICESat-2 moving forward. The first was done by Kelly Brunt, published last year, and she directly compared monthly ground-based GPS surveys from Summit, Greenland, which is an important validation site for ICESat-2, with the various IceBridge underflight flights that have occurred there over the past decade. And she found that they were all fundamentally compatible, and that's great. That means we're well set up to make a comparison there in the future with ICESat-2. Second, Catherine Walker has used IceBridge data and other ancillary data to show that glaciers in the western Antarctic Peninsula that previously had been stable for about 2 decades during the IceBridge era actually started to thin quite substantially, and that seems to be associated with atmospherically driven ocean warming. And then finally, Winnie Chu and others earlier this year published an examination of both IceBridge altimetry data, radar data, and modeling to map not just the total volume of the Fern Aquifer and porous snow in southeast Greenland, but also how that volume seems to change on an interannual basis. So just a few examples of how Operation IceBridge has helped support the ICESat-2 mission. And with that, I think I'll be opening the floor to questions. I'm not sure who our MC is.
Yes, right here.
There
Thank
we go.
you. We'll open the floor to reporters in the room. Please state your name and affiliation.
Seth Borenstein, the Associated Press. I think this would be for both Ben and Ron. In terms of results, and I know it's only been a couple months, you did tease us a little results. Can you tell us if there is anything surprising in terms of ice thickness in Antarctica, on ice shelves, Antarctica or Greenland, and on sea ice, especially Arctic sea ice, but also Antarctic sea ice? Are you finding it thinner than you'd seen because of the big gap between ICESat 1 and 2, despite, obviously you got, the bridge data. But in terms of for people, is this showing the dramatic melt we're hearing from other things?
Go ahead, Ron.
Well, we're only about 2 weeks of data, so what we've seen is the resolution of the ICESat-2 data, but there's nothing really surprising yet from just 2 weeks of data. I mean, but the sensitivity to the thinner ice is certainly remarkable.
I would say that the data are extremely promising, but we're still working on getting the footprints located. We're still in the calibration process for locating the footprints exactly. So it's premature at this point to compare the data to other data sets, except in the places where the ice is changing extremely quickly, and you can make those measurements with a fair amount of confidence. So I cherry-picked an example where there's been a lot of change. Trying to do more subtle measurements at this point is premature, but we're confident that the data will get there in the next month or 2.
All right, I think we have a question back here.
Thanks. John Finamos, BBC. Can we just talk about the bathymetry, because that's quite a remarkable result that you have there. Have you talked to anybody about the uses for that? Have you spoken to JEBCO, for instance? And they have this great undertaking 2030 to get the entire seafloor map. Now I realise you're only coastlines, or will be only coastlines here, but you'll be seeing very many remote areas that nobody has ever mapped before. So I'm just, what sort of depths are you getting to? Do you know?
You can fill in. We've seen some depths up to about 30 meters, but we haven't yet, like Ben said, our data isn't the science qualities that we can nail down an exact number for you now, but the potential is there, and it actually was quite surprising to us, given the low laser energy that we get to use because of the photon sensitivity of the detector. It was a little bit unexpected that we would see such penetration into the water, and certainly it depends on the water turbidity and the conditions of the water. So we've, again, cherry-picked a few amazing cases where the water is very clear, and so we get a lot of penetration. I think that the bathymetry, as I said, shows so much potential, and there's so many applications that it's going to be another exciting science discipline that ISAT-2 will support.
And in terms of coordination, what I would add in is we've been in touch with the USGS and with NOAA over the last several years about the potential for using green laser light for near coastal bathymetry, particularly places like Alaska, hard for them to get to do a thorough mapping. But we haven't reached out internationally yet to organizations like JEPCO, but I'm sure they'll be interested as well.
Are there other questions from reporters in the room?
Hi, Maddie Stone, Gizmodo. I was hoping that one of you could talk about the use for understanding forest structure and how the IceSat-2 data is complementing the JEDI instrument, which I know just launched as well.
Right, so ISAT-2, in terms of forest structure, as I mentioned, you get returns. You can retrieve a canopy height as well as a terrain height, so you're getting an actual tree elevation or tree height, which contributes a direct measurement to biomass estimation, which in a global scale. So what we're doing for the mid-latitudes for vegetation science is to not necessarily do repeat track measurements, but do an off-nadir or an off-pointing strategy to make sure that we provide a more uniform distribution of measurements around these mid-latitudes. Current collaboration with the JEDI mission, because it's very complementary. JEDI being on the space station after a successful launch last week will cover up to 51.5 degrees latitude and 51.5 degrees, well, north and south. So ISAT-2 covering those higher latitudes, especially in the boreal regions, will provide a truly global set. Since JEDI is focused on vegetation mapping, all of those measurements from JEDI as well as ISAT-2 will be put into the biomass estimate. So it's more comprehensive, more complete, and more accurate.
John?
How close are we to really robust maps of Antarctic freeboard? I mean, there are maps out there, but nobody really kind of shouts much about them because they don't have confidence in the snow loading. So, you know, when will we get there? When will we be publishing Antarctic freeboard in the way that we currently publish Arctic freeboard?
Well, we'll be able to get Antarctic freeboard definitely, and then we'll be able to get a lot more details. I think in terms of getting ice thickness, I think we're a little bit ways from getting there compared to the Arctic, but I think we'll be able to use. There are different promising techniques for getting snow depth, for getting actual ice thickness, but I think we're probably in the research bit of the process. But I think that, but the Antarctic is challenging because I think in depending on where you're trying to get freeboard and thickness, the Weddell Sea obviously has a lot more thicker ice, and that seems to be more amenable to doing things better. But the other parts of the Arctic, the Antarctic is more difficult because there are fewer in situ measurements for validating retrievals. So, but I think that's a big research goal for ISAT-2.
Are there any questions on the chat? Are there any other questions from reporters in the room?
Hi, Dave Klingus, Manga Bay. What's the estimated lifespan of ISAT-2, and do we expect this to be a long-standing series comparable to Landsat? What are the funding efforts for a more complete series?
So ISAT-2 has a mission requirement of 3 years. Since we had mass margin when we launched, they were able to fill the fuel tank essentially. So we should have fuel on board for much longer than that, on the order of 10 years. To your question about a longer term time series, our direction really comes from NASA headquarters. The last decadal survey that just came out in January of last year did identify ice topography and vegetation canopy structure using LIDAR as a goal for the next 10 years. So depending how NASA Earth Science Division chooses to move forward and implement that. I think the data here have shown that there's a lot of promise for new science discoveries with ICESat-2 that should just support and bolster the need for continued LiDAR missions.
Are there any other questions from reporters in the room? Are there any other questions on the chat? Okay, great. That concludes our press conference. Thank you very much.